Welcome to David Alexander Maths Tuition. This is Chapter 7E on methods of proof. Now in Chapter 7D we looked at proof by deduction, so that was when we were using logical and structured arguments to show that a conjecture is true. And in Chapter 7E we're looking at proof by exhaustion and also by counterexample. Okay, so here is an example of proof by exhaustion. So prove that the product of two consecutive cube numbers between 1 and 126 is always even. Okay, so there aren't that many cube numbers between 1 and 126. So, well, 1 cubed is 1, but that's not between 1 and 126. But 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. So you want to prove that two consecutive cube numbers between 1 and 126 is always even. So 8 multiplied by 27, well, we've got odd times by even, but let's just work it out anyway. 8 times 27 is 216, even. 27 multiplied by 64, 27 times 64, we know it's going to be even because we're multiplying by 64, which is even. 1728, even. And 64 times 125 is 8,000, which is even. There we go. So there is proving by exhaustion. Again, it wasn't a particularly draining list. There was only 4 cube numbers that we needed to play around with. Okay, by counterexample, prove that the following statement is not true. The product of two primes is always odd. So let's think of some prime numbers. 7 multiplied by 17. Okay, what is 7 multiplied by 17? 7 times by 17 is 119. Okay, it's odd. Okay, that's a bit annoying. I'm trying to prove that it's not true. Let's try, I don't know, 19 times by 3. 19 multiplied by 3 is 57, which is also odd. Come on, we can do better than this. How can I prove that this is not true? Well, think about the first prime number. The first prime number is weird because it's the only one that is even, 2. So let's just do 2 times, I don't know, any prime number will do. 2 times 17, 34, and we know that that is even. So therefore we have proved that the statement is not true because we found one counterexample that just blows that proof out of the water. The product of two primes is not always odd because 2 times 17 is 34 and that is even. Okay, so here are some other proof questions. So prove that when n is an integer and n is greater than or equal to 3 and less than or equal to 8, then m equals n plus 2 is not divisible by 12. Okay, so we're looking at the numbers 3, 4, 5, 6, 7 and 8, and when I add 2 to them I am going to get 5, 6, 7, 8, 9 and 10. Okay, well none of these are divisible by 10, so therefore I've proved by exhaustion that m is not divisible by 12 because as I've just said, 5, 6, 7, 8, 9, 10, none of them are divisible by 12. Prove that every odd integer between 2 and 26 is either prime or the product of two primes. So let's look at all the odd integers. So 3 prime, so I'll just put 3 is prime, 5 prime, 7 prime, 9, well that is the product of two primes, so 9 is just 3 times 3, so that's the product of two primes. 11 prime, 13 prime, 15 is, that's just 5 times 3, so that's the product of two primes. 17 is prime, 19 is prime, 21 is 7 times 3, so that's the product of two primes. 23 is prime, and what about 25? That is 5 times by 5, and that's the product of two primes. There we go, so we've proven that every odd integer between 2 and 26 is either prime or the product of two primes. Prove that the sum of two consecutive square numbers from 1 squared to 8 squared is an odd number. Okay, so two consecutive square numbers. So let's think of our square numbers. 1, 4, 9, 4 4s are 16, 5 5s are 25, 36, 49, and 64. So one plus 4 is 5, odd. 4 plus 9 is 13, odd. 9 plus 16 is 25, odd. 16 plus 25, I mean, we know it's going to be odd because we're adding odd to even every time, but let's just do the whole, do it out properly. So the next one is 25 plus 36. 25 plus 36 is 61, which is odd. 36 plus 49 is 85, odd. And then 49 plus 64 is 113, which is odd. So we can see that the sum of two consecutive numbers from 1 squared to 8 squared is always an odd number. Okay, so for this question we need to prove that for all real values of x, x plus 7 squared is greater than or equal to 6x plus 33. So we do need to be careful with some of these. Some of these are a little bit slippery. So what we're doing is we can expand the brackets. We can say that, actually we don't need brackets anymore. We can say that x squared plus 14x plus 49 is greater than or equal to 6x plus 33. Take away 6x from both sides, so x squared plus 8x and take away 33 from both sides is greater than or equal to 0, and this will go to factorise to x plus 4 squared is greater than or equal to 0. And of course anything squared is always greater than 0. But just because we've ended up with a true statement doesn't necessarily mean that we've started with a true statement. So we'll just call this our jottings. Okay, so what we need to do is just start at the bottom. We can say x plus 4 squared is definitely always greater than or equal to 0, because when you square something, it will always be positive. So therefore, if I expand the brackets, x squared plus 8x plus 16 will also be always greater than or equal to 0. Nothing dodgy has gone on between line 1 and line 2. So what I'm going to do now is I'm going to add 6x to both sides. So x squared plus 14x plus 16 must be greater than or equal to 6x. And now I'm going to add 33 to both sides. So x squared plus 14x plus 49 must be greater than or equal to 6x plus 33. And we know that x squared plus 14x plus 49 is x plus 7 squared, so we can therefore say so x plus 7 all squared is always greater than or equal to 6x plus 33. Seems a bit pointless just writing exactly the same stuff that we wrote before but in the opposite order, but the reason we're doing this is, as I mentioned at the start, just because we ended with something true doesn't mean we started with something true. So if we reverse it and we start with something true, then we can continue making sure that there's nothing untoward going on and we get to where we need to be.